Okay. So, dimensionality reduction refers to the reduction in dimensionality. What is dimensionality? Dimensionality refers to the number of variables data set might have. As you imagine your data to be a tabular data in the form of columns and rows, in which every column represents a variable and every row represents a new sample. So, as I said previously, you are at this stage in which you have obtained the data, you have pre-processed the data, you have done all the filtering and everything. Now you have the complete data. Now, once you have the complete data, it is free from null values, free from empty values, free from missing values, and your data is perfect in some sense. However, uh, before this step, what you were doing was you were putting in you missing values. Okay. So all the missing values were being brought in. But at this stage, we feel that the data that we have collected is huge, is enormous. So now at this point of time, we want to remove some of the information that is of no use to us, or probably no use to the problem at hand. Suppose I take an example. I have to this example I normally give to my student. I have to predict for any student what would the CGPA of that student in the upcoming semester. So suppose this is a prediction problem and I have to obtain data such that I can successfully predict what would be the CGPA, SGPA, semester grade point average of a student in the next semester. For that, I might require some information like past history, so current CGPA of the student, past SGPAs of the student, probably marks of his 10th and 12th examination, board examination. There are other factors like how much time he devotes to a study, probably how many friends that student has, indicative of how much time he devotes to his friends, how much time he spends on social media, how many mobile numbers he might have, etc. There might be so many factors which would combine together to conclude what would be the SGPA of a student in the next semester. It might help us to predict. However, there are some of the information related to a student which might be of no use to us. For example, the first name and last name of a student. Why do we care what is the first name and last name of a student if I have to calculate the grade point average of a student in the uh, predict the GPA of a student in the next semester? His name might be XY, his name might be Munindra Oja, whatever. Similarly, the mobile number. Okay, so mobile number, as I said, if the student has many mobile numbers, then that might be an indication that student is involved in too many activities and is actually not devoting sufficient time towards studies. However, if the student has one mobile number, let's assume the student has a mobile number, then why do I need the mobile number to understand what would be the GPA of a student in the next semester? I don't care what is the mobile number. Similarly, age of the student, date of birth of the student, address of the student, parents, siblings, number of siblings, all these are the information which might not be of great use when I'm trying to predict GPA of a student in the next semester. But still, if you collect data, all this information is related to the student. All this information might be useful to some other task, like how well connected this student might be. But at this point of time, if I have to calculate the grade point average of a student, some of the information might not be useful. So what we have done till now is that we are at the stage that we have collected all the data, all the information, possible information that we could get. We have collected all the information. Now our objective is to filter out that information which is of use to us, and just remove that information which is not useful. And what is useful, what is not useful is dependent upon the problem domain. What is the problem? What is the task at hand? What you are trying to predict? What you are trying to solve? So for this, we implement dimensionality reduction. There are other techniques also like feature selection for this purpose, feature selection or feature elimination. But I'll not get into that because feature selection and feature elimination actually involves the domain knowledge, and then you remove the information altogether. So suppose I just remove the number of siblings of a student, then I will have no way to obtain any small amount of information, knowledge from that variable. Howsoever minuscule that information might be, I have totally lost it. Contrary to that, in dimensionality reduction technique, what we do, we obtain the crux of all the variables, all the information, all the features of a data point, and then retain which is important and discard which is not important. Okay, so dimensionality reduction techniques are very useful and very important when you are trying to do a multi in a machine learning, trying to create a machine learning model, because i- with the presence of useless information, normally the machine learning model might not predict properly or give overfitting on some of the problems which are not desirable. So as it says over here, the number of input variable or feature for a data set is referred to as the dimensionality. More input feature often make a predictive modeling task more challenging, more generally referred to as the curse of dimensionality. Okay, the more dimension you have, the bigger the search space will be. Like if I assume that any sample has two variables, let's say length and width. So if a sample has two variables only, length and width, so it could be represented in a two-dimensional space. That's a graph, two-dimensional graph, 2D graph. Right? We could draw a point and on a plane, and we could represent this point. However, suppose this data point has three dimensions, three variable, three features, then we could utilize the services of a three-dimensional plot and point my data point somewhere in the 3D plot. Suppose it has four variables, then we will have to move into a four-dimensional hyperspace. We do not know what that space looks like. We are only able to visualize up to 3 dimension, but we are not able to visualize in four-dimensional and so on. So I assume that is a hyperspace. So four-dimensional hyperspace. Then gradually, if you increase the number of variables, number of features, thus number of dimensions, the representation of data point subsequently moves into that number of dimension. So suppose any data you have has got 20 feature values, 20 columns. It means that data point, if it has to be represented, will require a 20-dimensional space. And as you can easily imagine, if I have a two-dimensional space, the amount of space that I have to search, okay, to find the pattern will be much smaller than if I have to search a pattern in 20-dimensional space. Okay, so as you increase the space, as you increase the dimension, so you increase the space size, so you increase the complexity of finding the pattern in a bigger space. That is called the curse of dimensionality. As soon as you increase, add a new dimension, you have immediately I mean, many increase the complexity of the problem many folds. So this is what is called curse of dimensionality. That as soon as you add a dimension, and you must keep this point in mind, that adding a dimension is not random. You add a dimension, you add a feature to the data because you want that information. Okay. So first till now we discussed about why we need data, why we collect data, how to get data. And now at this point, from this point onward, I'm going to tell you that among the data that you have collected, I'm going to remove some of the data, because with more amount of variables, with more number of dimensions, our complexity increases a lot. Okay. So dimensionality reduction is about getting rid of uninformative information while retaining the crucial bits. So I'm not saying the data that you have collected is all useless. I'm just saying that for the problem that we are going to solve, whatever information we have, among that information, I will retain the crucial information while I will ignore the uninformative information. That is my job. Okay. And for that, I'm going to do dimensionality reduction, right? I hope this point is clear till now. So I move on with ignoring some of the introductory terms. Now, just a quick skip over benefits of dimensionality reduction. Space required to store the data is reduced as the number of dimensions come down. You have less dimension, then that leads to less computation or training time. Some algorithms do not perform well when we have a large dimension. So reducing these dimension needs to happen for the algorithm to be useful. It takes care of multi-collinearity by removing redundant features. Okay. For example, you have two variable time spent on treadmill and number of calories burned. So these two are correlated, related features, and we can have one of them removed and keep retain the other one. Now it helps in visualizing data because, as I said, we can visualize up to 3 dimension only. So if we reduce the number of features to 1, 2, 3, it will be very useful for us to be able to visualize it. There are different dimensionality reduction techniques such as feature selection or elimination, matrix factorization, manifold learning, and autoencoders. Okay. At this point of time, I will not discuss feature selection or elimination because of the just the fact that feature elimination and selection requires domain knowledge, and it is totally dependent upon the domain, the problem that you are solving. So with the help of a domain expert, you need to sit with the domain expert, and with the help of her, you should be able to identify which feature is useful and which feature is not useful to the problem, and just remove that variable. That is all we do in feature selection or elimination. Along with that, there are some other techniques also, like recursive feature selection, recursive feature elimination, in which what we do, we gradually increase number of variables, and then we try to observe the accuracy of the model. If the accuracy of model is increasing, we add the variable, otherwise we ignore the variable. That is recursive feature selection. Recursive feature elimination is the technique in which we keep all the dimensions with us, and recursively we remove one feature at a time. If the accuracy of the model increases or remains same by removal of a feature, then we remove that feature. However, if accuracy of the model decreases after removing a feature, then we retain that feature, we don't remove that feature. That is recursive selection or elimination. The biggest drawback with recursive feature selection or elimination technique is that as soon as you remove a variable, remove a dimension, you totally lose the information that was being provided by that variable, totally lose the knowledge. However, in dimensionality reduction technique that we are going to study now, we will not be losing the complete information. We will still get the um, kind of average information, a kind of feeler of every variable that we had. So we'll be discussing matrix factorization. Manifold learning and autoencoders are not discussed in this FDP, so I'll not go into that. So matrix factorization methods from linear algebra can be used to reduce dataset matrix into constituent parts. Examples include eigen decomposition, singular value decomposition, principal component analysis, linear discriminant analysis, and so on. The parts can then be ranked, and subset of those parts can be selected that best capture the salient structure of matrix that can be used to represent the dataset. Most common matrix factorization methods are support singular value decomposition and principal component analysis. I'll just skip manifold learning and autoencoder, and to give a brief introduction to linear algebra basics. We have a line. This is kind of linear classification in which we try to obtain the equation of this plane with which we are able to classify the given set of variables. Okay, and all the algorithms that we will study in this series of 3 lectures that I will deliver, the SVD, PCA, and LDA, we will be understanding it through the concept of linear regression or linear classification. Now, this part is important for understanding the matrix methodology. Suppose we have a matrix A and we have another matrix W. When we multiply a matrix A with matrix W and obtain a new matrix Y, so the equation W equal to Y states that when a certain matrix multiplies a certain vector, there is a certain outcome, that is Y. Now this matrix is also called a linear operator. We will treat this matrix W as a linear operator. So a name that makes it more apparent that a matrix is a linear little machine. So what we are doing, we are applying this operator W on a vector A. We call it vector A, but it is a constituent of the matrix. So any column vector of a matrix, we'll be treating that as a vector. So matrix is applied onto any vector A, we get another vector Y. So this is a linear operator, or we call it a little machine as well. This machine takes a vector as input and spits out another vector using a combination of several key operations such as rotating a vector's direction, adding or subtracting dimensions, stretching the vector, compressing the vector's length, and so on. Okay, this combination can be quite powerful for manipulating shape of the input space, and that is what is our objective. So if you have a matrix, you multiply it with another matrix and you get a kind of a skewed matrix, translated matrix. Okay, so matrix has been transformed to a different shape. That is our objective. We will somehow get the data. So data is now treated as the matrix, which we call as data matrix. So all the data that you have will have number of rows indicating of every observation, unique observation, and columns indicative of variables or dimensions of features. So the matrix which we obtain corresponding to the data that we have is called data matrix or design matrix. This data matrix will be multiplied with or operated upon with several matrices, several operators, which we will call a little machine. So these linear operators will work upon the data matrix so that shape of the matrix changes as per our wishes. When the shape of the matrix changes, then we will be able to find out new properties of the original data matrix. And with those new properties, we will try to understand which feature is important and which feature is not important. Okay, so I'll skip this as common knowledge, vector to subspaces, rank, dimensionality, and all these are just linear algebra basics which are discussed for students in the class. And I will move on to this part. Okay, eigen decomposition or diagonalizing a matrix. Using eigenvalues and eigenvector, we can decompose an n by n square matrix A into three subcomponents, and these three subcomponents I have represented them using V lambda, V inverse. Okay, now this matrix A has been decomposed into V lambda, V inverse, where uh, A is a square matrix, n by n square matrix. Okay, so this is very important that you must understand that we can decompose a square matrix only, which for which inverse is possible. There exists an inverse for this matrix. So A is a square matrix, and the inverse of A will exist only when the eigenvectors are linearly independent. So the inverse of the matrix must exist. If that is the case, then we can decompose this matrix into three components, subcomponents: V, lambda, and V inverse. And the multiplication of these three components will result back into our original matrix A. Okay. Now, what are these three subcomponents? We have decomposed this matrix A into three matrices, where the central matrix lambda is a matrix of eigenvalues. These lambdas are called eigenvalues. Lambda 1 is the eigenvalue of this matrix A, lambda 2 is the eigenvalue, and lambda 3 is the eigenvalue of this matrix A. such that all these eigenvalues are on the diagonal only. Okay, so it is a diagonalized matrix such that remain any value other than diagonal value is 0, and only diagonal values are having non-zero values. However, these values are the eigenvalues. So all the diagonal values are eigenvalues or 0, and non-diagonal values are definitely zeros. The matrix V is a matrix of eigenvectors. So as many eigenvalues, so many eigenvectors. So you can create these vectors, vertical vector, as you can see, v1, v2, v3, these are eigenvectors. And we create this matrix V with the help of every column will be an eigenvector. So suppose this matrix V has got 3 columns, it means it has got 3 eigenvectors, v1, v2, and v3. Will have 3 eigenvalues, lambda 1, 2, 3, that will fall on the diagonal, and then the V matrix has been inverted at the end and being multiplied to this V lambda, such that we get the original matrix. This way we can decompose our original matrix into 3 subcomponents, that is called eigen decomposition or diagonalizing a matrix. However, this is possible only if A is a square matrix and A has n linearly independent vectors. Okay, so when we say n in linearly independent vector, remember this n is coming from the dimension of the square matrix. Okay, so I should actually put it in under equation form. So I will just write it like this, right? So this is possible only if A is a square matrix and A has n linearly independent eigenvectors. So the dimension of this matrix A is n by n. It is a square matrix and n is the dimension. Now, as much how big the matrix is, those many eigenvalues this matrix should have, and all those eigenvalues should be linearly independent eigenvectors. Okay, will give linearly independent eigenvectors. Okay. However, this limitation is there because we can apply eigen decomposition only on square matrices. What happens if the matrix is not square, it is rectangular in nature? Then in that case, we implement singular value decomposition. Okay, singular value decomposition works on rectangular matrix, and it uh, okay, the question is why we decompose. I will answer. I will come to that. Okay, at this point of time, I'm just discussing how to decompose, and then I will tell you why we are decomposing it. Okay, so we are decomposing the matrix just at this point of time for the sake of understanding. Take it on faith that I will discuss it later why to decompose, but at this point of time I'm just discussing how to decompose, and then I will move on to why to decompose, and then immediately I will tell you the benefit of that decomposition. So I want to decompose with eigen decomposition. I was able to decompose a square matrix only. Now I want to decompose a rectangular matrix which is not a square matrix. I will need singular value decomposition to perform this task. Okay. Now, one of the most fascinating theorem of linear algebra proves that every square matrix, no matter what number it contains, must map a certain set of vectors back to themselves with scaling. Okay, and this is actually the equation of eigen decomposition, that is that is written as over here. Let A be an n by n matrix if there is a vector v and a scalar lambda such that AV is equal to lambda v, then V is an eigenvector and lambda is an eigenvalue of A. And the same thing is written in this theorem form, that every square matrix, no matter what number it contains, must map a certain set of vectors back to themselves. Okay, so this is the certain set of vector. V is the vector. So certain set of vector is being mapped to itself back to themselves with some scaling. Now some scaling is being performed and it is being mapped. So both of them, left hand side and right hand side, are equal to each other. However, right hand side has some scaling to it. In the general case of rectangular matrix, the matrix maps a set of input vector into a corresponding set of output vector, and its transpose maps those outputs back to the original input. This is what is the basis of matrix decomposition when we have a rectangular matrix. Okay. Now the square matrices have eigenvector and eigenvalues. For rectangular matrices, we will call them as left and right singular vector and corresponding singular values. Okay. So the same theorem can be represented again stated back in this fashion, that let A be an n by n matrix if there is a vector V and a scalar lambda such that A B equal to lambda V, then V is an eigenvector and lambda an eigenvalue of A. For rectangular matrix case, let A be a rectangular matrix if there are vectors u and v and a scalar sigma such that AV is equal to sigma u and A transpose u is equal to sigma v, then u and v are called left and right singular vectors, while sigma is called a singular value of A. Okay. So as it says over here, if you just read this line and try to map it with the second definition, you will understand what we are trying to say. The matrix maps a set of input vector into a corresponding set of output vector. Okay. Set of input vector AV is equal to sigma u, and its transpose maps those output back to original. So transpose A transpose u is equal to sigma v. Okay. So A transpose U, and it's into a corresponding output vector, and its transpose maps those outputs back to the original input. So A transpose U is equal to sigma U back to the original input. Then this U and V are called left and right singular vectors, and sigma is a singular value of. Fine. Taking that theorem and that definition in mind, we now apply a singular value decomposition technique on the data matrix that we have. So I'm trying to relate with the data that we have because we have to reduce the number of dimensions our data has. So when I'm talking about dimension, always keep this thing in mind that I'm talking about the number of columns. I have to reduce the number of columns of our data matrix. Suppose I have a rectangular matrix A. At this point of time, what is rectangular matrix A? Our data matrix. The data matrix that we have, I will treat that data matrix as our rectangular matrix A. And now I'm defining that any rectangular matrix A can be decomposed into three matrices of particular shape and characteristics. Okay. I call it as A equal to U sigma V transpose. Okay, so remember, this is not V transpose, this is this is not U transpose, rather it is V transpose, and U and V are two different matrices. So U and V are orthogonal matrices. These are the properties of U and V. U and V are orthogonal matrices. Uh, just, yeah. So U and V are orthogonal matrices such that U transpose U is equal to V transpose V, and that is equal to identity matrix. Okay. Sigma is a diagonal matrix containing singular values of X, which can be positive, negative 0 or negative. So this is the property. And now with this definition, we have to understand that any rectangular matrix A, and here I'm taking our data matrix as the rectangular matrix A. So any rectangular matrix A can be decomposed. Okay, that is written. So I am pretty sure that I can decompose my data matrix into three matrices of particular shape. And what those three matrices will be: U, sigma, V transpose. such that U and V are orthogonal matrices. Okay. So I don't know whether I will have U and V, how I will get U and V, but the property of U and V is that they have to be orthogonal, such that if they are orthogonal, it means U transpose U is equal to identity matrix and V transpose V is also equal to identity matrix. Now, if U and V are orthogonal matrices, the sigma matrix has to be a diagonal matrix containing singular values of X. Okay. So if this is the property of U, sigma and V, I can decompose this matrix A into U sigma V transpose such that I will be having three subcomponents of a bigger matrix. Okay. Now the second definition says if A be an m by n matrix with real entries and rank equal to R, there exists an m by m real orthogonal matrix U and n by n real orthogonal matrix V such that A is equal to U D V transpose. Here D is definitely this sigma. Okay, D is a part of constituent of sigma. So U D V transpose such that D is equal to, and you see this is sigma is on diagonal because there are some of the cases in which number of singular values are not sufficient to create the whole diagonal. So S1, S2, S3 up to SR, it might happen that there are some of the values are missing. So we put 0 in that case on the diagonal. So the D is sigma and diagonal on the sigma and 0 on the diagonal, and non-diagonal elements are all zeros. However, what is sigma? Sigma, it still is a matrix which has all the singular values on the diagonal only. So what it says about sigma, sigma is a diagonal matrix containing singular values of X which can be positive, 0 or negative. So this is the second definition. So A has been broken into three subcomponents, U, D, V transpose. Okay, where D is like this and sigma is like this, having singular values on the diagonal. D is m by n, sigma is r by r, and si's are real numbers such that s1 is greater than s2, greater than sr, and greater than 0. So you remember, see this property, you observe this property. If I could annotate, you see the first s1, that is over here. Let me make it red. The first S1 is greater than S2 and is greater than, will be greater than S3 and so on, such that SR is the smallest one. So I actually arrange it in a decreasing order. Okay, so the first value is the maximum, second value is the next maximum, third value is the third maximum, and so on. So this is how we arrange such that sigma is created. For a given matrix A transpose and A transpose A, these are two very special matrices in linear algebra. So what we have till now, what we have done till now, we have discussed what is singular value decomposition. For any given rectangular matrix, I will be able to divide it into three parts, break it into three parts, such that these two are orthogonal matrices, UV, and the central matrix sigma is a matrix of singular values, excuse me, matrix of singular values. Now we see what are singular values and singular vectors. Suppose I have a matrix A. Okay, so with these two transformation, A multiplied with A transpose and A transpose multiplied with A, definitely we will get two different matrices, as you all know very well know. So these are two different matrices, A transpose A versus A transpose. These are two special different matrices. However, they are very special matrices in linear algebra. And the matrix property of these two matrices are, these matrices are symmetrical, they are square, they have at least positive semi-definite, that is their eigenvalues are either 0 or positive. Okay, so they are at least positive semi-definite. Positive semi-definite means their eigenvalues are either 0 or positive. Both matrices have the same positive eigenvalues. They might have negative, they don't have negative values, right? Because they are least positive semi-definite. so they don't have the chance of having negative values. But if they have a positive value, the positive value of both matrices A transpose and ATA are same. The positive eigenvalues are same. However, it is quite possible that suppose AAT has a zero eigenvalue, but ATA does not have zero eigenvalue. That happens some of the times. But both will have the same rank R. Okay. In addition, the covariance matrices that we often use in ML are also in this form. So we will, as soon as we do this matrix transformations, we will get matrix covariance also, and which will be very useful to us in case of principal component analysis. Since they are symmetric, we can choose its eigenvector to be orthonormal, that is perpendicular to each other with unit length, and this is a fundamental property of symmetric matrix. Now, so we are given a matrix A, that is our data matrix. We can create AAT and ATA. Eigenvectors can be chosen to be orthonormal, and it does not need to be square, right? As soon as you perform AAT and ATA, the resulting matrix that you get is already a square matrix. So you have obtained till this point. Okay, Ms. Pushpa, I would request you to please mute yourself. Okay. So at this point, we have these terms: A, our original data matrix; lambda is our eigenvector; ui, vi, u, v, and sigma. A is the original data matrix. AT is the transpose of data matrix A. Ui is the eigenvectors of A transpose. Okay. So ui is the eigenvector of A transpose, and vi is the set of eigenvector of A transpose A. Capital U is the vectors ui concatenated to create a matrix U. Okay. What is V? V is a set of vectors of no, it should be Vi actually. Here I should have written Vi, and that is a mistake. Okay, V is the vectors Vi concatenated to create matrix V. As you can see over here right now, immediately you can see what is UI. UI is the set of eigenvector of AAT. So if I concatenate all the UIs, I get matrix capital U. And if I concatenate all the vector VIs, what are VIs? VIs are eigenvectors of ATA. I concatenate all of them as columns to get a matrix V. So U and V are two matrices. Capital U, capital V are two matrices. And now, if I have this, so what we will get? We will get these matrices U and V. We will immediately observe that they are orthogonal, such that their vectors are orthonormal, and it will be very easy to prove that U transpose U is equal to identity matrix and V transpose V is equal to identity matrix. Remember, at the point when I was explaining the SVD definition, I had told you that any matrix A can be broken into U sigma V transpose such that U and V have to follow this property: UTV is equal to identity matrix and VTV is equal to identity matrix. Now, what I have obtained over here is that I had that data matrix A, I created AAT and ATA. Okay. From AAT, I got this set of eigenvectors UI. I concatenated those UIs to create a matrix U. From ATA, I got the set of eigenvectors VI. I concatenated all VIs as columns to get our matrix V. Now this U and V have this property. They are orthogonal, so their vectors are orthonormal. They have this property that U transpose U is equal to identity matrix and V transpose V is equal to identity matrix. So immediately I have obtained this part of the singular value decomposition, right? Now, Since these vectors are orthonormal, it is easy to prove. Okay, we have proven that they are identity matrix. Sigma is now a diagonal matrix with R elements equal to the root of positive eigenvalues of AAT or ATA. Both matrices have same positive eigenvalues, so it does not matter. Now, so we have created U, we have created U, we have created V. How do we create sigma? This sigma, because I want to decompose our matrix A into three constituents. So we have created U, we have created V. How do we create sigma? Sigma is actually a diagonal matrix of eigenvectors, square root of eigenvector. So if lambda are the eigenvalues, square root of eigenvalue is the sigma, and sigma is called a singular value. So sigma is a diagonal matrix with R elements equal to the root of positive eigenvalues either of AAT or ATA falling on diagonals only. Okay. So the diagonal elements are composed of singular values. Now this is our sigma. This is our sigma having all the diagonal elements as singular values. What are singular values? Singular values are square root of eigenvalues. And definitely if the lambda 1, lambda 2, lambda r, it means they are arranged in the fashion that first lambda singular value, it is greater than sigma 2, sigma 2 is greater than sigma 3, sigma 3 is greater than sigma 4, and so on, such that sigma r is greater than sigma r plus 1, and finally we have the minimum singular value or 0 if it is missing. So now an m by n matrix can be decomposed as A can be decomposed as U m m, sigma m by n, and V n by n, V transpose n by n. Now this is the case. Okay, you observe this thing that A has been broken down into three subcomponents. Okay, what are these three subcomponents? These three subcomponents are created from our matrix A only. How do we obtain U? We obtained U from the matrix AAT. Okay, capital U. We obtained V from the matrix ATA. So you try to understand over here that everything is being created from matrix A only. Okay, so matrix A data points are being broken into three parts, three sub matrices. So A has been broken into U, sigma, and V transpose. U is created through AAT, V is created through ATA, and sigma is created through the eigenvalues, square root of eigenvalues that we obtained from ATA or AAT. And we arrange these eigenvector in the fashion that sigma 1 is greater than sigma 2 and so on, that I have already told you. Comparing to eigen decomposition, SVD works on non-square matrices. U and V are invertible for any matrix in SVD and they are orthonormal. To emphasize upon the thing that we discussed till now, let us do a hand computation and see how we decompose a matrix A into its subcomponent matrices. So suppose I want to find the singular value decomposition of matrix A. Then what we do is we have this matrix A. First we try to find AAT. AAT is 17, 8 and 8, 17. It's a square matrix, right? Now AAT and ATA will also be found out somewhere. So AAT is 17, 8, 8, 17. The characteristic polynomial is determinant. So if I have to find out the eigenvalues, I need to find out the characteristic polynomial. Determinant AAT minus lambda I is equal to lambda square minus 34 lambda plus 225, which can be broken into lambda minus 25, lambda minus 9. Now these two are the eigenvalues. 25 and 9 are the two eigenvalues of which matrix? AAT. These are the two eigenvalues, 25 and 9. And this example is chosen in such a way that we have a perfect squares as eigenvalues. However, in your case, it might not always be possible to get perfect square. So if they are perfect square, the square root will be 5 and 3 respectively. So the singular values we obtained, first singular value is the 5, second singular value is 3. Why do I call it first and 5 second? Because I want the first one to be the maximum. So maximum is 5 and second maximum is 3. Now we find right singular vector, the column of V, by finding an orthonormal set of eigenvectors of ATA. So eigenvectors of ATA are 25, 9 and 0. Since ATA is symmetric, we know that eigenvectors will be orthonormal. So for lambda equal to 25, we have ATA minus 25i, and we solve it so that we get V1. Unit length vector is kernel of this matrix. That's V1 equal to 1 upon root 2, 1 upon root 2, 0. For lambda equal to 9, the eigenvalue, we have final reduction. The unit length vector in kernel is V2. That is 1 upon root 18 minus 1 upon root 18 and 4 by root 18. Okay. So for the last eigenvector, we could compute kernel of ATA and in this fashion, uh, or we can find it as a unit vector perpendicular to V1 and V2. Both methods are possible. Just we need to find out the eigenvector. So perpendicular to V1 equal to ABC, we need minus A equal to B, so that if we multiply, we get the um, dot product to be 0. So then using this condition, V2 transpose V3 equal to 0 becomes 2a upon root 18 plus 4c upon root 18 equal to 0. That is minus a equal to b. Okay. So we have two eigenvectors. Remember, 1 by root 2, 1 by root 2, 0, and 1 by root 18 minus 1 by root 18 and 4 by root 18. These are the two eigenvector with, and I want to find third eigenvector which is perpendicular to these, both of these. So if a vector is perpendicular to both of these, what I do, I need to find a vector which is perpendicular to them. Okay. So using this method, I could get V3 equal to my A minus A upon n minus A by 2. So this solves V3, and to get the value of A, we can implement it into, we could get the perpendicular with 1 by root 2 as well, such that we get, for it to be unit length, we need A equal to 2 by 3. Okay. So V3 equal to 2 by 3 and minus 2 by 3 and minus 1 by 3. If we substitute A in here, we get the V3 as 2 by 3, minus 2 by 3 and 1 by 3. So we have obtained three eigenvectors. V1 is 1 by root 2, 1 by root 2, 0. V2 is 1 by root 18 minus 1 by root 18 and 4 by root 18. And while V3 will not be part of U, okay, because U is AAT and AAT has only two eigenvalues, so two eigenvectors, while ATA has three eigenvalues, 25, 9 and 0. So it will have three eigenvectors. That is why we performed this computation, so that we get the third eigenvector. And third eigenvector is over here. Third eigenvector for us is 2 by 3 minus 2 by 3 and 1 minus 1 by 3. At this point, we know what we know. We know U. How do we know U? U is a concatenation of eigenvectors of U. What were the eigenvectors of U? V1 and V2. Where is V1? V1 is obtained over here. Uh, yes, 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. Okay. So we have calculated the vector uh, AAT. Okay, AAT. So we created vectors for the third matrix V. So V1, V2, V3, V1, V2, V3, 1 by root 2, 1 by root 2, 0. And remember, this is the transpose. Okay. So the vector is this 1 by root 2, 1 by root 2, 0, 1 by root 2, 1 by root 2, 0. This is a column vector. So if it is a column vector, if we create a matrix out of column vector, it should be in the column. It should be in the column. Okay. It should be like this. It should be like this. However, you remember we have U sigma V transpose. So this is actually transpose. So if it is a transpose, so instead of having it like this, what we find that the column vector has been transposed to become a row vector. So instead of this, what we find that first eigenvector is in a row instead of being in column. So first row is the first eigenvector, second row is the second eigenvector, this one by root 18 minus 1 by root 18 and so on, and the third eigenvector is part of the third row. Okay, so if we have u, we have sigma, we have v, we can obtain u, and thus u is with this formula sigma u equal to AVI that we had obtained above, sigma u equal to AVI. Remember, I had told you this thing at the definition only. If let A be a rectangular matrix, there are vectors u and v and a scalar sigma such that AV equal to sigma u. Okay, AV equal to sigma u. So now we have AV equal to sigma u. So sigma u equal to AV. If I have to find u, then I take this sigma down. So ui equal to 1 by sigma AVI. And with this, I could calculate u equal to 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. So now in its full glory, there is singular value decomposition. Matrix A has been decomposed into three matrices where the first matrix is U, second matrix is sigma, that is matrix obtained by taking square root of eigenvalues and putting them on diagonal. And see, although it is on diagonal, this is not a square matrix, so not all diagonal values will be fulfilled. Only first diagonal, okay, second row again at the diagonal because at the center, and I don't have third row over here. Okay, so don't assume that it will always be a square matrix. It is a rectangular matrix, the sigma value. So 5 3 is are falling on the diagonal and they are square root of eigenvalues. So we have sigma, and the third matrix is the matrix V transpose that we obtained over here. So what we do to summarize for the given example, we had A, we calculated AT equal to this, A transpose A equal to this. These matrices are least positive semi-definite. All eigenvalues are positive or zero. They share the same positive eigenvalue 25 and 9. We obtain their singular values. So if we obtain the eigenvector of AT, we will obtain U1 as 1 by root 2, 1 by root 2, and 1 by root 2 minus 1 by root 2. That is first matrix. For ATA, this matrix, we obtain its eigenvalues as 25, 9, and 0. The eigenvectors are these three. And for that, we have our corresponding V transpose as this one. So A matrix is broken into three subcomponents U, sigma, V transpose. What is the physical significance of having these matrices? The physical significance comes over here. Okay, when you understand these four fundamental subspaces of a data matrix, there is a column space, there is a row space, null space, and left null space defined for any matrix. Okay, so a way to dissect a matrix is via the four fundamental subspaces. These are column space, row space, null space, and left null space. The column space says that set of output vector S where S is equal to AW as we vary the weight W's. What is mathematical interpretation? All possible linear combination of columns. Data interpretation, all outcomes that are linearly predictable based on observed features. The vector W contains weight of each feature. However, the left singular vector corresponding to non-zero singular values, a subset of columns of U. Okay, so column space refers to the left singular vector corresponding to non-zero singular values, subset of columns of U. What is left singular vector? When we perform the singular value decomposition, the matrix U is called the left singular vector. Okay, these are all vectors constituent of U. So these are called, because they are on the left hand side, so they are called left singular vectors. The vectors of V are called right singular vectors. Okay. So column space is actually the left singular vector corresponding to non-zero singular values. So any value, any singular value which is non-zero, corresponding to that, whatever vector we obtain are called the column space that constitute our column space. What are row space? A row space set of output vector R, where R is equal to UTA. Okay, and it is all possible linear combination of rows. In the data interpretation, we see a vector in the row space is something that can be represented as a linear combination of existing data points. Okay, so it can be interpreted as the space of non-novel data. So vector U contains the weight of each data point in the linear combination. So what is happening over here? This row space is actually uh, interpreted as the space of non-novel data. Novel data is that data which is ideal data, and we get this data all the time. However, in any pattern, we are not looking for novel data. We are looking for unique data which is very different from the existing data, because we want variance, and that will be again be the basis of principal component analysis. So with the column space and row space, and you see what is the basis of this right row space? Right singular vectors corresponding to non-zero singular values. So with row space and column space, what we are actually getting over here in SVD is that with the column space, I'm talking about all the columns which correspond to non-zero singular values. So it means both of these rows of the matrix U. When I'm talking about row space, I'm talking about all the columns which correspond to non-zero singular values. It means only two rows, okay, first row and second row, because third row corresponded to a zero singular value which will not be used, right? So only those columns, means in this transpose matrix, the first two rows corresponding to non-zero singular values. However, it has a value which is zero, so I will not consider that. So only two columns will constitute the row space. Okay, then we have null spaces and left null space, which means that set of input vector where AW is equal to 0, which means the right singular value vector, singular vector corresponding to zero singular values, and left null is left singular vector corresponding to zero singular values. Okay. Now at this point of time, what we have done, we have divided our data set into four parts. One part corresponding to matrix U having non-zero singular values. Second part having matrix U with zero singular values. Third part matrix U with non-zero singular values. And fourth part, fourth space corresponding to matrix V with zero singular values. So with this definition, what I'm trying to emphasize upon is that any data point corresponding to zero singular values will not be of any use to us, because that is not going to affect the linear combination of the columns or rows. So vectors that are orthogonal to all column. So all those vectors which are orthogonal will not affect the property of a vector. Okay, because if something is orthogonal, the multiplication, the dot product becomes zero. Okay, so that is not at all going to affect it. So left null space as well as the null space is not going to put any effect on the property of your whole data set. So if I'm able to remove null space as well as left null space from the data matrix, I will be left with lesser number of columns, and that removal will not have any effect on the overall knowledge, overall information, overall predictability of the model. Okay, so with singular value decomposition, my objective is to find out four spaces. row space, column space, null space, and left null space. Out of these four spaces, I will remove the null space and left null space such that I am left with only column space and row space. Fine. And how do we identify? We identify it with zero singular value and non-zero singular value. Zero singular values of u and v, and non-zero singular values of u and v. These are the four spaces. So anything corresponding to zero singular value, either belonging to left matrix u or right matrix v, we will remove them. Okay. Now, so data with a large number of features may be reduced to a smaller subset of features that are most relevant to the prediction problem. This results in a matrix with lower rank that is said to approximate the original matrix. So if we are removing something, what we are doing is that the leftover matrix is approximating the original data matrix. When we performed SVD operation on the original data, we select the top k largest singular values in sigma, and these column can be selected from sigma and rows from the matrix V transpose. An approximate B of the original vector A can then be constructed as B is equal to U sigma VKT. Okay. Now how we are going over here? We created this decomposition. Okay. So to answer the question in which it was asked by Aurobindo Paul that why are we decomposing? Okay. Now I am able to answer this question. First, what we did, we decomposed the original data matrix into three submatrices, U, sigma, and V transpose. Now from that, I was able to find out the zero singular value and non-zero singular value. In this example, there is only one matrix V which has zero singular value. But with that also, I'll be able to give this example that the zero singular value and its corresponding columns are ignored. Okay. So we will ignore zero singular values. So what happens in this? Let me annotate. In this matrix, sigma matrix, I have 5, I have 0. I have 5 and 3. These are two singular values which are non-zero. And then I have a third column over here. Okay, third column. What if I have to remove this third column? Okay, if I remove this third column, the matrix multiplication from sigma versus V transpose will not be possible because it will be a 2 by 2 matrix and it is a 3 by 3 matrix. Okay. So what happens? I will remove the third row also from VT. I'll remove the third row, right? So if I remove the third row, what happens now? So let me just put it as black. Suppose I remove the third column, okay, and then I remove the third row because I won't be able to do this matrix multiplication if it has 3 rows because I have 2 columns only. Okay, so column by row. So now this is a 2 by 2 matrix, the U matrix. Second is also 2 by 2 matrix. Okay, and third one is a 2 by 3 matrix. So matrix multiplication is possible because a row and column matches. So if I have to get this, why I'm removing the third column of sigma? Because I don't want zero singular values. So I will remove this because I am removing the null space. After removing it, I will remove this column of sigma and third row of V transpose such that I will get an approximate matrix. This approximate matrix will be, now over here, I can say that B is equal to, B is an approximation of A, U, complete U. Sigma is a truncated sigma. So let us call it sigma t, and then Vt, which is the transpose. The original transpose is also truncated because one row has been removed. So now instead of A which was originally A was U sigma, and V transpose has been converted to B, where B is U sigma truncated and Vt truncated. Now, if they are truncated, it means what? Some of the information has been left out. Okay. And what information was left out? All the null space, all the information corresponding to zero singular values have been removed. Now, this B is an approximation of A because A was equal to right hand side. Right hand side has been approximated into this right hand side, and this right hand side gives me B. So B is actually an approximation of A. That is what is written over here. And that is why we decompose a given data matrix into three parts. Then using the singular values, value of singular values, if it is non-zero, we retain it. If it is zero, we remove it. Even after retaining non-zero singular values, we can make this choice that we can retain only significant sized singular value. Significant sized means suppose some singular value is 10, 20, 30, 40, something like that, and there is a singular value like zero point 0.2, 0.31, something like that. Then with respect to 50, a singular value of 50 and a singular value of zero point 0.1, the singular value which is corresponding to value zero point 0.1 can safely be ignored. Even if it is non-zero, I can ignore it. So it totally depends upon you that how much approximation you want to do, that you can remove some of the singular values and their corresponding columns from sigma. We perform SVD operation on original data and select top k. Okay, so top k largest singular values in sigma are selected and remaining columns are removed. These columns can be selected from sigma and the rows, corresponding rows, from VT. Fine. Now, whatever approximation we perform, we call it matrix B, and this matrix B is an approximation of matrix A, which will be the final output on your data matrix. Okay, this way we were able to remove some of the values, some of the columns which were not necessary. Okay. Now we will take, and I hope this information was useful. You were able to understand what is singular value decomposition. I know in this lecture I talked a lot about the theoretical aspect. However, starting the next lecture, which is going to start at 10:30, I will discuss the implementation part as well, and then I'll move on to principal component analysis. In the first lecture, the establishment of linear algebra basics is very important because then only we get to understand what we are doing and what is happening. So I hope it was useful to all of you, and you got something out of it. And I will end the session. I will leave right now. The session will continue. In the next session, I will start at 10:30, and then I will continue with the implementation part of SVD as well as principal component analysis discussion. Okay. Any question at this point of time? I can take questions if you have any. Okay. I think there are no questions, so I will just end it over here, and we will proceed on with the break, and then we will meet again at 10:30.